identified in the claim checklist. Uh, can I request everyone to mute, please? Yes, thank you. So the claim checklist is a checklist published by the Radiology AI Society, the journal, in fact, which mandates some components as important while presenting an AI solution for publication. And this article found that more than half of the papers didn't even meet the three mandatory criteria from the checklist. And around 55 of the 62 papers, which again further qualified from this inclusion criteria, found to have a high risk of bias. And more shockingly, only 12 papers used a truly external validated test set. And in fact, one of the algorithm went on to even present their test results on the training data. So even though none of these papers followed the sanity, which is usually should be followed while presenting the results of an AI solution, but they all went through because of the pandemic and because of the what I would call as a scientific leniency, which most of these journals followed. And despite having invested in so much time, money, and researcher work, none of these solutions were ever used in clinical practice. We are at the nearly, I would say, at least the vein of the pandemic, at least in India. So, and then we are part of a large radiology group, and it's sad to say that despite having the opportunity to, exposure to many of these solutions, we couldn't use even one of them in our clinical practice. That actually brings us to the important point that why context is an important component in AI development as well as validation. I will begin with this X-ray. This is a classical COVID X-ray. All radiologists would easily identify it. So there are bilateral, near symmetrical peripheral opacities, a mixture of ground glass densities and consolidation. You present this X-ray to any radiologist now, they would easily say that this is a COVID X-ray. Now let's move on to this X-ray. This is also a somewhat similar X-ray, but the lesions are slightly fainter. You can again see that there are some faint peripheral basal consolidations and mixed ground glass densities. So will it be another case of COVID-19 pneumonia? Not really. Actually, this was an X-ray from 2018. So way before even the pandemic started. So what happens when you feed both these X-rays? Let's assume a hypothetical situation where you are feeding or giving these two X-rays to a human reader and an AI solution which classifies, which predicts presence of COVID on chest X-rays. The human reader is well aware of the fact, or at least knows the fact that this X-ray is from this pandemic times, so he would have no problems in calling this as a COVID-19 pneumonia. But if he is aware that it's not from this pandemic times, he's definitely not going to call this as a COVID-19 pneumonia. But what happens when you run an AI solution on same two X-rays? It's going to call both of them as COVID-19 pneumonia. So it's so easy to understand, but it's the finer print which has been missed in developing all these solutions. None of the AI solutions which have been presented during these pandemic times, more than 2,000 of them have been published. The studies have taken into the consideration the most important criteria, the pre-test probability. The context in this scenario, which I presented, in a very simplistic manner, I should say, just to drive home the message very clearly, is the time of the presentation, right? The AI algorithm doesn't take into consideration what's the context of the time in which the X-rays is being done, whereas a clinical person, a radiologist, would always have that information at the back of his mind. There are several such parameters of context. It could be clinical symptoms, it could be age, demography, comorbid conditions, addictions, habits, so on. All these contexts are figured into a single indicator called pre-test probability, which a practicing radiologist would always take into consideration before diagnosing any imaging study. But none of the AI solutions, let it be the commercial ones or the academic ones, have the option or even have the ability to ingest this pre-test probability before throwing out a prediction. That's a major lacuna which we should understand. The contextual AI, in fact, is based on 4 broad principles. The number one, intelligibility, adaptivity, customizability, and context awareness. Intelligibility is the ability of the algorithm to explain itself to the users. There are 2 elements to it. I will briefly touch upon this. And the adaptivity is the ability of the solution to run in a different situation or environment, but still meet the user expectations. It's kind of overlapping with the concept of generalizability, but there are some finer differences there. Customizability is the ability which the algorithm offers to the user to take control of the solution, to alter the thresholds and other parameters, tweak the other parameters to kind of use the solution based on its needs. One good example would be, in some instances, we want a solution to be used as a screening solution where we want the solution to be very highly sensitive. We are fine with the false positives in that scenario, but we don't want to miss out even one single case. A classical example of population screening studies. But the same user might want to use the solution in a highly specific condition where he doesn't want too many false positives coming in. He's fine with some of the milder or minor cases getting excluded. This is a typical use case for COVID triaging scenarios where we want to choose patients we want to treat based on their severity or their clinical symptoms. But again, sadly, none of the commercially available solutions offer this customizability option to the user. They always come with a fixed threshold. And the final most important component is the context awareness. According to me, that's a core requirement, because the solution should be able to see the case in the same way that a radiologist or a human reader or even a medical person in a different context would approach the problem. Touching upon one of the biggest news for radiology AI this year, the WHO, the World Health Organization, approved use of 3 commercially available algorithms, very popular algorithms, very good algorithms, for screening for TB in remote locations in the place of human readers. I would say that this is a very landmark moment, or a very important moment for everyone working in the radiology AI space, because an organization like WHO approving the unsupervised use of AI solutions is something all of these companies have been dreaming about. But there are problems in this, right? When you go and read the recommendation of the WHO, it says that it recommends using these solutions in patients 15 years or older for both screening and triage for TB diseases. That's where the problem starts, right? When you're applying the solution both for screening and triage. I will take a moment here to explain the finer difference between triaging and screening. Triaging is the process of deciding the care pathways for people based on their symptoms, signs, and other comorbid conditions. Whereas screening is one done on a normal population, right? You take a population of 1,000 people completely asymptomatic or maybe symptomatic and run a test to identify people who would be taken into the care pathway. So that finer difference is being missed out by this recommendation. So what happens here is, again, we will go back to the hypothetical situation. There is a human reader and there isn't this AI which the WHO recommends. They are both presented with the chest X-ray solutions. The human reader is presented with the chest X-ray solution, the clinical features of TB. So he's therefore going to place this case as having TB higher than other diagnoses. But if there are no clinical information, or if there is no possibility of TB, he is less likely to call this as TB. But whereas the AI solution that WHO recommends is not going to take into this consideration, and it's going to call anything, even having any feature which is a little bit even closely resembling TB as having TB. This is perfectly fine for a screening situation, but not for a triaging situation. In fact, the study on which this entire recommendation was based upon used a test set of adult patients with symptoms suggestive of TB, clearly not a screening population. These are patients who had clinical features of TB, and they have tested these three different algorithms. The CAT for TB, LUNAT, and QXR, very popular algorithms, excellent algorithms. And they found that they are nearly as accurate, or in fact, much better in accuracy in some instances as compared to radiologists, and they have went on with the recommendations. But the problem still remains. These algorithms were not tested on a screening population. They have been tested on patients with clear-cut symptoms of TB. What happens in that case is, right, the AI would definitely score better than the humans in the triaging situation, whereas you can't say the same thing about the screening because the context brings in for the humans, the context awareness reduces their specificity because if they are aware that the context in which the case is presented is not typical of TB, they are going to call it as less likely to call it as a TB and score less than the AI algorithms. That's the fundamental problem with all these algorithms, which are doing this human versus AI comparisons without even presenting the same kind of context which the humans are presented with to the solutions. So again, there's a final difference between the findings and disease, which I wanted to stress to all the developers here. Findings could be like anything like a consolidation, nodule, or effusion. This is a perceptual task. You see a lesion, you see a scan, you identify that there is something problematic there. That's the lesion. It's not dependent upon the context per se. But when you are converting these findings into a disease like COVID-19 or pneumonia, it's very much context dependent. It's a cognitive task, and humans score much better than the AI in these instances. Touching upon briefly upon the intelligibility or understandability, it actually denotes the characteristic of a model to make it understandable to the humans. And there are two components to it. One is model understandability and human understandability. And these two X-rays here would be able to drive home the message. These are two X-rays. Humans would call both of them as completely normal. We have tested these two X-rays on many commercial algorithms. All of them ended up calling the X-ray on the right side of the screen, on the left side of the screen, as having some kind of opacity in the right lower lung. Because if you see closely, there is absence of a breast shadow in this X-ray, which the algorithm sees that as having an opacity on the right side and calls them as a consolidation. This is a classical example. If there is an explainability model which kind of maps this kind of breast opacity as a consolidation, the humans will be able to kind of know why this algorithm is calling this as a consolidation and make their own informed choices. This is very important because the bias which is being built in these algorithms will be scaled up if that's the humans are not aware of why the particular algorithm is giving that output. And also, such recommendations by WHO ends up systematizing the bias, because if both the AI solutions which have been recommended by the algorithm was trained on the same data set, the both will kind of have the same biases, and the bias will be perpetuated across the deployment sites, and it will become normalized. That's the thing which all developers need to fight against and work against, avoiding bias while building these algorithms. So I'll just kind of briefly touch upon a couple of our works in this area before closing this talk. This is the paper which we published last year in the academic radiology journal, where we tried to understand the chest CT algorithm, which identifies nodules and classifies them as malignant and benign based upon the heat maps which are produced by the algorithms. We used a technique called occlusion, where different parts of the image were occluded, and the drop in the probability scores were mapped to a heat map, and a set of radiologists were presented these heat map lesions, and the imaging attributes to these heat maps are determined to see if we can go back in time and to predict based on the heat maps whether this particular heat map belongs to a benign nodule or a malignant nodule. It was a very interesting work. I recommend the participants to go and read this work and reach out to me if you need further classifications on that. With that, I will kind of close my talk. Before closing it, I want to drive home three key important points. The AI which is being built for medical applications should be context aware. They should take into consideration of the context in which the particular scan or the imaging study is being performed, and the bias which is being introduced during the training process should be mitigated by both the developers as well as the validators by focusing on the understandability models that are being built with the AI development. And we need to have appropriate audit tools and techniques for such evaluations to be performed in the deployment sites. Thank you so much. I will take any questions.
Doctor, are you working on which algorithm for this image processing?
So this algorithm which I presented to you was by a company called Predible Lung, which is a startup based out of Bangalore. And we work with several collaborators, sir. Almost every big company, every big small company in the radiology AI space. We focus more on the radiology space, almost exclusively in the radiology space, not the other aspects of the medical AI. And we work with almost every one of them. I think we also have some conversations going on with cases. Mosia is here, so we also are in early talks with their company. I don't know if Mosia.
Okay. Madam, can you unmute the speaker? Can I unmute the mic? Dr. Mona.
Sorry. Yes. So I'm. Any other questions, sir? So we can go to the next speaker. We have with us our second presenter, who is Mosia Agbalesi, a PhD student at Sorbonne University with INRI. She's from the National Institute of Research in Digital Science and Technology in Paris. Mosia graduated in 2018 with a Masters of Science in Modeling and Simulation at Paris-Saclay University. Her PhD thesis is co-funded by CASIS, a French company which provides software solutions for medical imaging processing, namely cardiac simulation and image software. The topic of the PhD is modeling and patient-specific fluid structure interaction simulation on aortic pathological configurations. So Mosia hopes to provide assistance for medical diagnosis through simulations, and she's very passionate about patient-specific simulations of biomechanical systems. So over to Mosia, who shall share her experience with estimation of the mechanical state of the aortic wall with 4D flow MRI. Welcome, Mosia.
Do you hear me?
Yes, we do. Thank you.
Okay, thank you. Thank you for giving me the chance to talk about this interesting work. So today I'm going to present part of an interesting work that could that is very promising about the estimation of the mechanical state of the aortic wall from 4D flow MRI. And this is prior to, let's say, AI application. So, so this part of the work, this is a small part of what I'm doing in collaboration with Dijon University Hospital in Bulgaria, Sorbonne University, and especially INRIA, which is a National Research Institute, and CASIS SAS, which is a French company providing a solution for medical image processing and AI also. And also working with Tohoku University. So, okay. So this is briefly what I'm going to talk about. So first, a bit of introduction to give you the clinical context of this work. Why is it important? Present you the problem that we want to solve and how we're going to solve this problem. And also show you some small validation case on a 2D case that is a synthetic test case. And then the application to a real 4D flow data set from a patient, and give you some conclusion and perspective on also limitation of this method. So why do we want to estimate the Lagrangian, the mechanical state, let's say, of the aortic wall. Why? There's a clinical context for this. First of all, something that we notice is that the guidelines relating the diameter of the ascending aorta to the risk of aneurysm and dissection is being increasingly questioned. So now physicians are investigating more hemodynamical biomarkers to understand the risk of aneurysm and dissection. So which means that we need to compute wall shear stress and related biomarkers. One of the good practice to do that would be to use blood flow simulation. This is what is done, because you can have more accuracy, space accuracy, and time accuracy for your calculation. So we need to do not only simulation, but patient-specific blood flow simulations. And which patient-specific? 4D-Flow MRI. And I will explain you why. 4D-Flow MRI is very interesting because it gives you patient-specific blood flow data. So which framework are we going to use? This is the main question. And in most articles, when you have blood flow simulation, we use CFD. Let me tell you why it can be tricky, because for the aorta, there is a coupling between blood flow and the aortic wall motion, because the aortic wall is compliant. So the most natural way to do that would be to use fluid structure interaction, which models this coupling between the structure and the fluid. And you have dramatic differences between the result that you can have with CFD and with FSI. So we chose to use FSI to have more realistic simulations. But the problem with those simulations are how do you add the patient data in this? So usually what you can see in the articles is that you will impose an inlet profile or do some very sophisticated mass lumps model at the boundary to take into account the rest of the circulatory system. But yes, for us, it's too complicated. We have 4D flow. 4D flow is velocity everywhere. It's kind of complete data. So we want to do something so that we can also estimate, so that we can also correct the motion of the wall and the velocity, the blood flow from 4D flow data. But 4D flow data won't provide you the displacement of the aortic wall directly. So this, and for the computation of the biomarker that we're interested in, we need to have the motion of the aortic wall. And I will explain why. First of all, for those who are not familiar with, what is 4D flow MRI, also called CMR? So 4D flow MRI will give you, it will basically give you 4 kind of images. So you have anatomic series, which are the grayscale images of a part of the body, and you will also have the velocity in 3 orthogonal directions. And with that, you can also sometimes a physician will also have MRI acquisition before 4D flow, and this is something that you can use, but not only. So here I show you just a volume representation of 4D flow, which is nicer, it's cooler, let's say. So how do we estimate the mechanical state of the aorta, which means displacement and deformation? We estimate this with the grayscale images, the time-resolved grayscale images, the flow images, and a geometry, which can come from MRI, but not necessarily. You need just to have one patient-specific geometry. So why is it important? As you can see here, imagine that you have your CFD simulation. CFD is like blood flow, but with a fixed geometry, to make it simple. As you can see, during the cardiac cycle, the aortic wall is moving. So your computational domain should be moving. So if you compute if the blood flow inside this region to have your wall shear stress, then the wall is not the real wall. So it's inside the flow at some point of the cardiac cycle. This is why it is important for us to track the deformation of the aorta. So the problem is quite simple. We want to estimate the point-to-point deformation of the aortic wall during the cardiac cycle before doing any kind of blood flow simulation. And how do we want to do that? We want to use a patient-specific geometry as initial state data. We want to use extensively not only the velocity series from the 4D flow, but also the anatomic series, the grayscale images, because it gives you some geometrical information, and those flow series will give you some kinematical information. We want to combine all this to track the deformation of the aorta. So the algorithm, so I'm a mathematician, so I will give you some mathematics stuff, but it won't be very long, don't worry. So we are interested in finding a deformation, let's call it phi, of the aortic wall, but not only, Lagrangian means that you have point-to-point match in time, not only independent geometry that have been segmented, but you have kinematical information with this. So we want to find the Lagrangian deformation of the aortic wall, but not only this, we also add the velocity to define a mechanical state. And we want to find these deformations such that we minimize a misfit to data. So those data are geometrical data, which are, let's say, embodied in this psi m. And this psi m will be generated from the images. And we also have a misfit to the velocity data, which is um of psi m. And with all this, we also add a kinematical constraint, which is the most simple method that you can have to regularize the velocity, because it can add some noise. So first of all, you will ask me a simple question. Okay, Mosia, you have images. How can you get a geometry with those images? This is very simple. We use a very simple method that is very close to active contour, if it is not active contour. And so we want to maximize, we want to find, let's say, to find a contour that is close to a prior, the phi tilde, but with a regularization. So this is the delta with the gradients, with the surface gradients. To make it simple, we want to find a contour on the images, which is close to a certain prior and which is regular. This is quite simple. And so to explain why this is important is that, so this is just to explain the idea, but I will go very fast to have the time to go to the aorta. And so the first step, as I told you, is to convert the images into geometrical information that we can use for our algorithm. And so to do so, we use a splitting technique. So if we want to write let's say the equation that we are going to solve to have our observation from the images, it's very non-linear, and we don't want to do that. So we're going to split the function that we want to solve into two parts. And using a splitting techniques, we're going to have this regular surface that is being generated from the images. And it's called psi m. And then we use some space discretization of your choice, and some time discretization, because you don't have something that is continuous in time, but you have a time sampling. Let's say, for example, 20 frames per cardiac cycle. So you have some time discretization, some space discretization, because you are using a mesh. And so this leads us to a discrete formulation of your problem that has the same form of the continuous formulation. Of course, it's the same problem, that you want to have a mechanical state of the aorta, which minimizes a misfit to the 4D flow data that you have processed with a certain dynamical constraint to regularize the velocity. Okay, and how are we going to solve this? We use a very well-known Kalman filter for sequential state estimation. So Kalman filter will decompose into a prediction correction step. So you have an initial geometry, initial state that has some uncertainty because you have one segmentation coming from MRA, which is an average segmentation. You don't know exactly if it fits the computational domain, but it is your best guess. So you will give this to the Kalman filter. We'll iterate on a prediction correction step. Prediction by applying your dynamical constraint. Correcting with 4D flow MRI, and then you will generate mechanical state estimation, iteration after iteration. You will improve your estimation. And so, having this technique, so Moshe, it's very well what you've done, but how can you show me that this will work on the aorta? So we try to create in synthetic case, sorry. So we simulate the flow of, we simulate the deformation of immersed vesicle in a cavity with fluid, which has a deformation much more complex than the aorta. And with this, we are able to generate the same kind of data that you have with 4D flow. So with our simulation, we are able to recreate grayscale images as you have for magnitude series. And since we are solving a numerical example, then you have the velocity everywhere, of course, because you solve the velocity. So we have the same kind of data that we have for 4D flow MRI, which is very interesting. Then we can compare and see how the method should perform. We can play with the noise. We can test the method to its limits. So as we did this, we realized that the most important thing to have good accuracy of the overall surface, good overall surface accuracy, is the quality of the image, which means the image gradient. If the image gradient is good, then you will have overall good similarity between the real aorta and your estimation. But because of the noise, because of the velocity noise, you can have different local behavior, which means that it will affect the quality of your tracking, as you can see here. Here you have when you have sigma v is equal 0.003, it's low noise on velocity. And when you have sigma v equals 0.105, you have huge noise. So you see that on the overall surface similarity, it's quite close. You don't see any difference. But on the local tracking, you have some difference. So what is going to fix this difference is your regularization parameters. And you can say, oh, but I'm not a mathematician, I'm a physician. How am I going to play with this to have something good? What we realized with this test is that you have two ways to play to regularize and to have a good tracking of the deformation of the aorta. You can play on the regularization of your model or the regularization of your observation. But something that is very comfortable for you, I think, is that when you play with the regularization of the model, you are limited because at some point you will reach a point that your method will be very unstable. But when you play with the regularization of your observation, then you are limited in the range of variation of those parameters. So which means that you are more stable in a sense. So we find a good way to set those parameters to be very useful for physicians to understand what they are doing exactly, to have to master this technique. And then this is the part that you all want to know. Is this is very nice, but is this working for the aorta? Let's see. So we have, so thanks to Dijon University Hospital, we had a 4D flow exam of the patient. So with MRA, we were able to have our initial configuration. So we have the images, the flow images, and the magnetic series. And so first of all, let me show you why we need MRA, or at least one patient-specific geometry that has been well segmented. Because we also want, for simulation, we also want to have the carotid vessels. But on a magnetic series, on the quality that we had, we were not able to segment this from properly from 4D flow series. So this is why we need to have this initial configuration from MRA. So this is being improved thanks to Cassis' work to have a first segmentation that is not using MRA, which is quite impressive. So we applied this method to the aorta, and this is what we got. Yes. So as you can see, we are able to, as you can see, we are able to track the deformation of the aorta. With some things to be improved, of course, but we are able to track the deformation of the aorta, to track the deformation of the computational domain. And in this example, what I want to show is that the method is quite sensitive to the environment of the aorta, because the aorta is not the only vessel with blood flow. You have also the pulmonary artery that are closed. And so we need also to find a way to improve this, and AI could give some good perspective in this way. So to finish with, I will give you a last simulation that I really like. So this aorta is moving, deforming, and that we're able to reconstruct. So briefly, as a conclusion, so 4D flow MRI is a very interesting medical image, because it provides a complete information to track the deformation of the aorta, which was not that obvious in the beginning. So magnetic series will provide you geometrical information, flow series kinematical information, and with Kalman filter, we're able to convert this to have a local strain estimation of the aorta, which can be very interesting. So we have promising results with one patient aorta. So we are ongoing clinical validation. The method has some limitation because it takes 30 minutes. So we need to improve the speed of the method. And the perspective for this method is that it can be applied, it's not specific to the aorta, it can be applied to any organ with 4D flow MRI. And also it can be, the point of using this was to calibrate FSI simulations. And we are actually working on that intensively, on a very new method to get rid of all approximation for inlet condition, to have something very close to 4D flow MRI. And this technique will still be part of a commercial solution provided by Cassis. So this is all for me. Thank you for your attention. Do you have any question?
Thank you so much, Mosia. That was really extensive. And not only that, you brought us back to all the mathematics. And I'm sure it's the correct place to be speaking all that maths amongst all these engineers. But for some of us, it was like really a lot. But it was brilliant.
Yes.
Thank you.
Dr. Mona, with your permission, can I call Casey Jain for next presentation?
Yes, absolutely.
Okay, thank you so much. Thank you so much, Mosia. It's a really very nice presentation. Even I also worked on biomedical signal processing in my doctoral degree. So it's interesting because I worked on the same area. Okay. So hereby I request Engineer Casey Jain for next presentation.
Yes, he's joining.
Sorry?
He's joining.
Okay, he's joining.
Yeah, he's preparing his presentation and then he will.
How much time they will take?
Yes. He's preparing his presentation and he will be joining shortly. The PPT.
So do I call for next presenters?
No, just he will join. Just.
Okay.
How many presenters are there? Madam?
There's just one more.
One more. Yeah. No time restriction for them?
How long is your presentation, Pranav?
It won't take me more than 15 minutes.
आर्टिफिशियल इंटेलिजेंस और नीचे
ये
जी
कुछ नहीं है इसमें, सब ब्लैंक कलर। Ma'am, you start with the other presenters and I'm preparing the slide here.
Sure.
Okay.
Right. So the last of the speakers is Dr. Pranav Ajmera, as from the radiology side, and he's from Dr. D.Y. Patil Medical College, Pune. He has. You could hear me, right? Yeah.
Yes, ma'am.
Yeah. So he's from D.Y. Patil Medical College, Pune, and he has an active interest in neuroradiology, functional MRI, and artificial intelligence. Following a fellowship on functional MRI from MGH USA, he has been involved with, actively associated with nearly 2 years with Deep Tech as a clinical researcher, during which he has authored 9+ index publications. Deep Tech in itself is leveraging AI for medical imaging. Deep Tech is based out of Pune, India, and has 3 products, which is Augmento, an AI-powered PACS, Genki, a public health screening tool, and Deep Tech Teleradiology, which is powered by AI. So using these 3 solutions, Deep Tech aims to improve productivity and minimize errors in radiology reporting. Dr. Pranav shall now be presenting to us what are the real-world deployments of AI in radiology workflows. Over to you, Dr. Pranav.
Thank you so much for the elaborate introduction. I hope my screen is visible.
Yes, it is.
Okay, that's great. So a very good afternoon, everybody. I'll be straightforward going away to the presentation. I'm here to talk about the real world deployment of AI in radiology workflows, because as we know, there are lots of models out there, but not many of them actually are able to find their way into real world scenarios where they have clinical utility. So while they are probably great on paper, but if there is no clinical utility, then was it really worth the money? So before I go further, just a bit about, just a minute. Yeah, before I go further, just a bit about AI. I'm sure everybody already knows about it, but just to sum it up, AI is the usage of specific algorithms to train computers for completing specific tasks by processing a large amount of data and by recognizing specific patterns in the data. Over here in a Venn diagram, we can see that there is a very close association between machine learning, natural language processing, and robotics. AI, being the superset, encompasses the subset of machine learning and deep learning. In fact, deep learning is a realm under machine learning, which has grown explosively in the past couple of years and is receiving a lot of active research attention. And the models can be the kind of training can be supervised, could be unsupervised, or can be reinforcement training. These are the most prominent of the methodologies. A machine learning model is the output generated when you train your machine learning algorithm with data. After training, when you provide a model with an input, you will be given an output. While deep learning is an artificial intelligence function which imitates the workings of the human brain in processing data and creating patterns for use in decision making. with the ability to understand data from the lower level all the way up the chain, a deep learning algorithm can improve its performance over time and can arrive at decisions at any given moment in time. In fact, a lot of AI models which are currently being used in radiology are actually from the realm of deep learning. CNN is a class of deep feed-forward artificial neural network, which has successfully been applied to analyze visual imagery. And they too were in fact inspired by biological processes. And we can see that a scan goes through multiple layers, layer after layer, until finally we get an output. Machine learning involves, in fact, a large variety of possibilities. And the three most prominent ones include artificial neural network, deep learning network, and the ensemble network. A bit about data processing. So data processing can be cloud-based, can be on-premise, that is at the site itself, or can be edge-based. An edge device is essentially a high-grade, industrial grade PC with high-grade specifications, and which is rugged and robust and can be employed in mobile vans and thus can reach all the way up to peripheries. So moving on to the actual scope of radiology applications in imaging. Now, to understand that, we need to understand that all the existing models which we have, most of them perform a very narrow task. And most of these tasks can be grouped under three larger categories. These include the perceptual category, that is the perceptual tasks, tasks which involve reasoning, and tasks which involve processing. While till date, very limited amount of time has been given to develop tools, AI models, which actually help with reporting, administration, and acquisition. And actually, successful model tool would be something which can actually perform multiple of these functions together simultaneously. Moving further, despite the large proportion of attention which has been provided to develop such models, the current models remain very limited in their applicability. And in fact, many of the models which have been created by large universities and developers perform exceptionally well on a limited set of data. But when you put them to test on the larger community, their performance is often subpar. And in fact, some of them are so often complicated that they cannot be integrated as a part of a larger deployable network. So deeming them virtually great on paper, but not clinically utilizable. And as Dr. Venugopal already mentioned about the Nature article, the article actually beautifully summates that how during the pandemic, despite the fact that a lot of researchers were actually involved in building models, and a lot of models actually came into being, received publication, received citations, the actual clinical utility was still not much because they cannot be deployed in real world scenarios. So there's a lot of untapped potential in terms of, as I mentioned earlier, three main areas. These involve reporting, administration, and acquisition. And AI models need to be there, which can actually take care of either all of them simultaneously, or at least be tailor-made to focus on at least one of them. For example, there are tools which do all the models which we currently have, they provide us with output in some form of graphs and tables, but not many of them actually are able to integrate it inside a radiologist report. So while the tables and graphs, they're all good, but if they cannot be put inside a report, then the actual clinical utility for the clinician is not much, because then again, he'll have to go right from scratch typing in the report. So what an ideal case scenario would be that the model actually generates a report, assesses the entire scans, puts it inside a report, keeps the format ready, and the clinician, all he needs to do is verify. And I'm fairly sure that it's easy to understand that it takes way lesser time and effort to verify a scan than it takes to do something from scratch. Administration is another major area, and this essentially includes applications which can support the scheduling and can balance the workload of radiologists. Lots of time, especially on teleradiology, many radiologists are available, but there are a large variety of scans also, but the matching process never happens. There are scans which need higher priority, and there are scans which could maybe wait a while, but there is no essential way to prioritize the scan. And if we cannot prioritize the scan, then it might so happen that some patient who actually needs urgent care is denied so. So the actual goal needs to be to create not just a single model or a single application. It needs to be to develop an entire platform, a super platform, which has multiple AI models performing in sync with each other, and they have a real world clinical utility. So moving further, here's an example of you can say a PACS, which has an AI model integrated onto the server. So I'll be talking about this in detail further, but just a glimpse of it. So what essentially it is doing is it is triaging all the patients. So the red one needs a very high priority, while the yellow ones are somewhat medium priority, and the green ones can wait a bit. So in case the radiologist is really pressed for time, this can help him out and can also benefit the patient, because this patient definitely needs urgent care. So AI is basically out there to play the role of a traffic policeman and make sure that a scan gets the kind of priority and this kind of time it needs. Now, moving on to the complete example of how an end-to-end platform will actually look like. So on the left side, we have data being generated from various CT scanners, X-ray machines, and mobile-based X-ray machines. All this data goes on to a cloud server in case of mobile X-ray vans, whereas in case of hospital-based facilities, it goes on to PACS, that is picture and archiving and communication system, that is the workstation. This DICOM data is then uploaded onto a cloud-based server, which is also linked to the hospital information system, the HIS. And all the data, all the patient data is essentially protected by a big firewall, and access is limited and provided to only those who will actively play a part in the patient management. So once onto the cloud, now the cloud provides it a lot of flexibility in terms of having multiple AI platforms loaded onto it. All the AI models have a specific role. So while all of them are narrow in essence, but having many of them function simultaneously ensures that a single report goes through is triaged for various pathologies. And this ends up with providing us with a report which provides us with the pathology the particular patient might be suffering from. And it also helps us to generate data, analytical data. The reports so generated can then be directly signed off by the radiologist, who is the human in the loop. So it is essential to have him because he will be verifying the final detail. But since everything is already in place, it will take him way lesser time to do the needful. Once it has been signed off, the report can automatically be sent in an electronic manner. Now, this can be via an email or can be via WhatsApp, even an SMS notification. And it can be sent to the treating physician, the patient, and even the management. In fact, such a platform has a huge role to play when a pandemic such as COVID hit. Reason being that having a cloud-based server provides us with a lot of data. And if a report has been triaged or screened to be COVID positive and it is finalized by the same by the treating radiologist, then it can be directly linked to the national dashboard and sent to the government. So this would actually generate data quicker and also allow the government to assess the extent of the disease currently prevalent in the amongst the civilians. But behind the curtains, there's actually a lot going on, and developing such a model actually requires a very close association between the domain experts, namely the doctors, and the people who actually develop the model, that is the data engineers, the data scientists. A typical algorithm lifecycle involves multiple steps, starting right from data curation, moving on to data annotation, processing, algorithmic assessment, validation, deployment, and external validation. And even if one step goes wrong, we might end up with a model which does not perform what we intended to be done. And in fact, the one step which needs a lot of attention is the external validation, because a lot of models which are actually built are validated either on a single institution or even on the same training data. So that is not true validation, and that will never really allow us to assess whether or not that model will perform well in real world scenario. So moving on to an actual use case example. So we developed a tool called as Genki, and this AI model was essentially developed to screen for tuberculosis. And we undertook this project in collaboration with the Greater Chennai Corporation. And the corporation lent us mobile vans, which were equipped with X-ray machines. You can see them over here. And alongside the X-ray machines, we also had an edge tool right over there inside the machine, integrated over there. So what exactly the project was, I'll talk about in the next slide. But the results was that over a span of a couple of months, we screened over 1 lakh people, and nearly 7 vans were utilized for this process. And the TB model, which was performing, had an accuracy of 0.92, a sensitivity of 0.9, a specificity of 0.93, and an area under curve around 0.96. The advantage was in terms of yield, that the number of patients who were finally chosen, or you can say directed for CBNAT, the yield of such patients actually went up from 20 per lakh to 500 per lakh. How the entire project was conceived and developed was can be seen in this particular slide. A patient just needs to walk in to the van, and a patient just needs to walk up to the van and provide the person with the basic registration details. Hardly takes a minute. Once this has been done, the patient goes inside. There's a trained technician who takes the radiography shot. And once this is done, the radiograph automatically goes goes through the edge device, which screens for tuberculosis. And all of this takes less than 1 minute. Once this has been done, then the data is also simultaneously uploaded onto the cloud server. And for this, we don't even need very high-end Wi-Fi connections or anything. A simple 3G connection would suffice, and we do have that available at most places now. If the tool felt that the findings were actually suspicious of tuberculosis, then the patient was immediately directed to get a sputum or a swab done. And in case the screening results came out negative, the patient could walk free and go about doing his regular job. Once on the cloud server, again, the patients who were screened to be positive, notifications were sent to the Greater Chennai Corporation. And the officials got in touch with the patients to follow up with them closely to see how the CBNAT results turned up. Again, this can also be integrated in case a national dashboard is created, because such a tool would allow such a cloud platform would allow all the data to go directly to the results of the triage to the government in case of a pandemic like COVID, and for diseases such as tuberculosis, which might have a great benefit both to the patient and the government in controlling such diseases. Just an example of how the triage was performed. All the ones in greens are the healthy ones, and the ones in red are the TB suspect. So moving on. This platform was then later on evaluated by Friends for International TB. This is an organization based out of Vietnam. And the results were that out of 11 competitors, our model performed quite good, and in fact was amongst the top two. And the specificity, sensitivity, and accuracy is up there on the screens to be seen. So moving on to a very significant problem actually that lots of AI models face, and even we faced initially. And that is the problem of model decay, data drift issue. So different machines tend to have different settings and different image quality. And an AI model which is trained solely to recognize data from one machine might falter if it is provided data from another machine. So over time, how we have conceived the model was conceived, and I mean, we have been developing this model is that initially in phase 1, all the patients which were triaged as positive were sent to the treating radiologist to have a look and classify it as, I mean, give a diagnostic report of what they felt. In phase 2, only a select few of the scans, 20 to 30% scans, were reviewed by the radiologist. And currently the TB model is in phase 3, as it has been performing significantly well and has improved a lot over time. Since it's a deep learning model, it has learned actually a lot over time. And as of now, 5% of all the scans are audited by the radiologist to confirm the AI accuracy. A similar model is being trained for COVID to detect COVID-19, but it is actually early on and is right in phase 1. So we have also developed a lot of algorithms, and as I already showed, the Genki one to detect TB. There are models to detect COVID-19. The models to detect pneumonia, knee osteoarthritis, foreign bodies, fracture, pneumothorax, fibrosis, emphysema. While if they were just to exist on paper, they could never really be utilized clinically. However, integrating all of them together on a platform allows us to scan each and every radiograph for each of this pathology. So the chance that a radiograph, I mean, any particular finding is based on a radiograph is less, and the final work which needs to be done by clinicians and radiologists actually goes, I mean, is actually decreased. So the chances that they'll actually use the platform and the AI algorithm, that the chances that they'll actually start to trust the platform go up significantly. Here's just a slide of all the models which we have currently, and most of the ones currently are traced on lung, since there's a lot of data generated on chest radiographs and CT. And with this, I would like to end my talk. Thanks a lot for being patient.
Thank you, Pranav. Are there any questions? So the Deep Tech has been doing a lot of work in AI, and it's great to see all the 3 aspects of your platform. And over to you, Dr. Vandana.
Yeah, thank you so much, ma'am. Now I invite Engineer K.C. Jain sir for next presentation.
Yes, ma'am, he is here.
Yeah, okay, okay. He's chief engineer. He worked as a chief engineer, Government of Botswana. He worked as a chief engineer at Government of Zimbabwe, Southern Africa. And he's currently working as a visiting professor, Gyanganga Institute of Technology and Sciences, Jabalpur, in Civil Engineering Department. So over to you, K.C. Jain sir, for your presentation. Yes, okay.
इसको बढ़ाते जाना फॉरवर्ड करने के लिए बैठ जाएंगे तो यहाँ बैठ जाता हूँ एक स्लाइड को बढ़ाते जाएंगे
Screen. Sir, ma'am, you can see the slide and it is changing.
Yes, sir.
Okay, okay.
मैडम बोल रही है आप इस पे बैठिए
आप कर लो, आवाज भी आएगा, आप कर लीजिए।
Good evening, everyone. Myself, Engineer K.C. Jain. I'm retired from Government of Zimbabwe and Government of Botswana in Southern Africa as Chief Engineer. I'm a fellow of Institution of Engineers India, a life fellow. Today, I'm presenting at this 34th National Convention, use of artificial intelligence in civil engineering. It appears none of the branches have left where artificial intelligence is not used. In civil engineering, when we look at China, I think the way they are doing things, 30-story building in 2 months, it's all AI. AI is the technology associated with the simulation of human intelligence in machines to enable learning and problem solving. Artificial intelligence makes the decision-making process simple, fast, and efficient. It incorporates a whole set of operations in civil engineering to enhance the construction process and changes the way engineers and builders work. The traditional methods vis-a-vis artificial intelligence, these used for modeling and optimizing complex systems, consume considerable time and computing resources. But AI-based algorithms provide better alternatives to solve problems in civil engineering. The data required to develop AI algorithms are obtained using programmed machines like drones, smart cameras, smart sensors, etc. The data is analyzed to determine all possible construction aberrations and anomalies. Compared to traditional methods, AI in civil engineering brings significant benefits to engineering design, analysis, and construction management. AI algorithms also use trial and error methods to identify the best process that needs to be followed depending upon on-site conditions. Hence, such implementation for project execution improves the quality and productivity of the overall project. Importance of AI in civil engineering. The basic idea behind incorporating AI and automation in civil engineering is to perform a task using algorithms and machines in a more efficient manner than what is expected from humans. Artificial intelligence algorithms have the potential to help the construction sector overcome challenges and improve overall productivity and efficiency. What are the advantages of AI in civil engineering? It prevents cost overruns, reduce the risk of accidents, monitor and prioritize the risk on job site, efficient project planning, and increase in productivity on job sites. But there are disadvantages too. AI is expensive, and there is always a fear of rise of unemployment in a country like ours, India. AI techniques in civil engineering, the common techniques which are evolutionary computation, EC, artificial neural networks, ANNs, fuzzy systems, and expert systems. Evolutionary computation, it is a subcategory of artificial intelligence being used in civil engineering for several decades. It was an iterative process and is an effective method to solve complex optimization problems. The standard evolutionary algorithms used in civil engineering are genetic algorithms, GAS, artificial immune systems, AIS, and genetic programming, that is GP. Artificial neural networks. The neural networks collect, memorize, analyze, and process massive amounts of data obtained from experiments or numerical analysis to provide basic solutions to complex engineering problems. It has widespread application in studying building materials, structural and geotechnical engineering, construction management, and identifying structural defects. Fuzzy systems. It's a tool for adopting the human way of thinking and problem solving when dealing with uncertain issues faced in construction projects. It considered several aspects like the quality of material, equipment, logistics, and physical risk directly related to administrative and financial capacity. Expert system. It is widely used in construction engineering, underground works, geotechnical engineering, geological explorations, disaster prevention, material engineering, and petrochemical industry. This method relies on existing knowledge and human expert to set up a knowledge system. The system focuses on a particular area and uses all the corresponding knowledge and experience stored in the programming system to solve complex problems. So in conclusion, AI is the engineering. Thank you very much. Bye.
Hello. Samir.
Sir, thank you very much for your words of wisdom. I now, before coming to the conclusion, I invite co-chairman of today's function, Dr. Shailja Shukla, madam, for summing up.
Thank you, Dr. Vedant,
Thank you.
for providing me this opportunity to be a rapporteur of this August convention, that is 34th National Convention of Computer Engineers on industrial and medical application of artificial intelligence. So on this platform, we are very thankful for providing such knowledge by field experts of their field, medical field, radiologists, academicians, engineers, and really we got a lot of knowledge by the different areas focusing the application of AI in imaging and medical image processing, etc. So I would like to summarize the different renowned speakers focused on different area. So first speaker, Dr. Vasant Venugopal, focused very nicely on contextual AI on this pandemic era, pandemic time. So basically, he focused on various areas like what are the common pitfalls and recommendations for a radiologist and how AI solutions will provide a correct solution to the existing problem using various models of deep learning and how the different COVID cases of pneumonia, 2080, 2020, etc., they were used for correct prediction when different models of AI were used, and of course, the both AI models and of course the correctness by the practitioner physicians is very important. So he has very nicely presented the various aspects which are important in contextual AI, like intelligibility, that is very important. Then adaptability, one cannot ignore this. Then customizability, and what are the context or awareness. So very nicely, sir, you presented the knowledge about what are the contextual AI, role of contextual AI in the pandemic time. Thank you very much for providing such a wide knowledge of your field. Thank you very much. Now, after this, the second speaker, expert, she is Moshel Egbales, and she has focused very nicely on medical image estimation of mechanical state of aortic wall from 4D flow MRI images. So basically, she has taken various model and algorithms of mathematics and taking the combination of models and images, how the prediction can be done. It is very nicely explained by Moshel, and she has defined a framework for patient-specific blood flow simulations by taking a model, and also in this model, what should be the requirement, that is aortic blood flow, patient specifications, boundary conditions, which cannot be ignored to develop a complete model to define a complete objective functions under different practical constraints. So really, that was a very nice insights by taking a well examples of MRI images, and also surface positions space. She has nicely described the surface position, space, and time discretization of the model, then how to develop discrete formulation of the problem by using these constraint and objective functions, and also sequential state estimation with Kalman filter that gives a good result. So really very nice speech and knowledge were given by the expert, and also the simulation results for 4D MRI were explained nicely on a estimation on a real patient data, and really that will provide a forum for all the experts which are connected on this platform to work more on these emerging areas. So thank you very much. And also after this, the third speaker, Dr. Pranav Ajmera, will with Dr. Amit. He focused basically on real-world deployment of artificial intelligence in radiology workflow. So really, we all engineers, academicians, and the different participants who are connected in this convention are benefited by your view, your knowledge, your expertise. Basically, Dr. Pranav focused on how AI can be unboxing AI using different models like machine learning, deep learning, convolution neural network, and how data processing is important in real workflow. So in his speech, he has demonstrated very well that how also, smart AI-enabled workflow gives a very correct results in integration of physician, radiologist, patient, and administration, of course. And also, this all information goes to national dashboard systems for the correct information and database formation. And also, he focused on that role of domain expert as well as data scientists and data analytics are very important in all this development of model and predictions. So thank you very much, Dr. Pranav, for focusing on various aspects of real world deployment of artificial intelligence in radiology. Also, he has developed some use cases example by his own Genki model. So we got some insight into this model also. And finally, we are really very much thankful to Dr. K.C. Jain by giving information on how artificial intelligence is very useful in various application of civil engineering like geotechnical engineering, remote sensing, construction, etc. He also explained insight into neural network, deep learning, machine learning, and fuzzy systems, which are decision-making systems to make the decision-making very perfect. So thank you, Dr. Jain, for giving us insight into the civil engineering and how artificial intelligence is very much useful in modern era in civil engineering. So I hope all the participants, all the people who are connected and really benefited by the knowledge given on this common platform. And also I would like to thank Madam Bhatia. Although I think from very starting from 2 p.m. she has connected. I know she might be very busy, but still thank you very much on connecting with us on this platform. And we hope in future also you will be connected with us on such forums. So thank you, madam. Thank you very much.
Thank you so much, Dr. Shailaja. That was excellent. And I love the way that you actually put together all the talks of the afternoon. I think that was a brilliant, method. And maybe we should also do this in radiology, where after a session, we make a repertoire of everything. Really good. It was wonderful being here. Thank you so much. And it was very nice to present amongst the engineers. And we hope to continue to collaborate. Thank you.
Thank you.
Thank you for a good reporting of the conference. Shailaja Thakur has presented well, reported well all the speakers' presentation. Hope this conference will give us a very good information for every one of us. Thank you for our organizer. Thank you.
Thank you, Dr. Siddharth. Thank you, everybody.
Thank you, Dr. Siddharth.
Thank you. Thank you.
Thank you very much.
Thank you, Mr. Veda.
Yes. Thank you very much, Dr. Mona Bhatia, madam, Dr. Shailaja Shukla, madam, and Dr. S. Siddhappa, sir, Dr. Varuna Roy, madam, Mr. Pranav Ajmera ji, for your kind cooperation in making this session successful. Thank you, sir. Thank you.
So
Thank
there is
you
one
all.
minor correction.
Thank you so much.
It's not S. Siddhappa, one correction. It is not S. Siddhappa, it is M. Siddhappa.
Sir, what I'm not able to hear.
You please make a correction while sending the certificate.
Acha, sir. Correct, thank you.
Yes, yes,
S.
yes.
SE.
It is not yes, it is M.
It's
Sir,
M.
sir,
Oh.
you can correct it yourself, sir. If you see the right-hand side, there in the panel, your name is there. So if you click there, you can change you can rename, or I can also do it for you. But if you had told me previously, I could have changed it for you.
Okay, okay, sir. Okay, okay.
Okay. Yes, sir. We will definitely.
Uh-huh.
Although Madam said for M, I thought when introducing Vandana Roy, Madam said for M only. But I thought she's making some. We
Yeah.
have written written records also. We were
Yes,
having.
yes, sir. We could have changed it, sir.
Yes,
So, thank you, sir. Thank you.
Thank you.
Thank you. Okay, sir. So we come to the conclusion of today's session.